We're talking about taking the temperature of a generator's rotor.
And look, it seems pretty simple, doesn't it? I mean, just stick a thermometer on it. But
just try to imagine the environment inside a generator. It's hostile. The rotor is spinning at up to 3,000 RPM, creating these immense forces and stresses. It's completely bathed in powerful electromagnetic fields that mess with any sensitive signal. You can't just run a wire to it. I mean, it's spinning. And you can't just slap a battery on there that you have to change all the time. It is quite literally a perfect storm of engineering challenges.
Indirect methods is built on one simple, fundamental physical principle. See, the copper windings inside the rotor have this amazing property. Their electrical resistance changes in a very predictable way with temperature. For every single degree Celsius the temperature goes up, the resistance of that copper goes up by a very specific 0.393%. It's like having a thermometer built right into the machine itself.
This little formula is the mathematical engine behind the entire indirect method.
By constantly measuring the voltage and the current that's being fed into the rotor, just like you see here, we can calculate its resistance in real time. That gives us the key variable that we need to plug into our other formula. But there's a catch: precision. While this method is really clever, it's just not perfect. Tiny errors in sampling the data or in accounting for resistance from external cables, they all add up. The result? A typical accuracy of plus or minus 15 degrees Celsius. That need for better precision is exactly what led to the next step in the evolution here: direct methods. This is where cutting-edge tech lets us stop calculating and start measuring directly. Wireless telemetry. A tiny sensor unit gets mounted right on the spinning rotor shaft. Then, a stationary unit outside the machine beams energy to that sensor, a lot of times using ultrasonic waves. The sensor takes its reading and sends the temperature data back, again using coded wireless pulses. So you get no wires, no batteries to change, just clean, direct, real-time data. Now here's another incredibly cool approach that uses magnetic fields. So some rotors have permanent magnets inside, and the strength of a magnet's field actually gets weaker as its temperature goes up. So by placing a really sensitive sensor outside the generator that can precisely measure the field strength, you can accurately figure out the internal temperature.
We go from an error margin of 15 degrees all the way down to just 3. That is a 5-fold increase in accuracy. And that kind of precision, well, it lets operators run the generator closer to its optimal limits and catch potential problems much, much sooner.
For more detailed explanation on this topic, please visit blog page through the link in the description.